Okay, so yesterday I kind of quickly went through the first 4 exercises on the first sheet. We didn't get around to doing the 5th one, but it's kind of nice and we can probably do that now and then we can look at the second sheet. So it maybe gives you a bit of time to look at the second sheet and get some ideas already. So but it's short. So there's probably a little typo in this question. We should stick absolute values around everything here, otherwise it doesn't really make sense. You could just multiply everything by minus one. So in part A, we're asked to show that there is some constant that bounds the absolute value of multiform at every single point in the upper half plane up to some factor involving the imaginary part. So the idea here is to look at what happens first in the fundamental domain. We can say something useful about that. We can then try to extend that by modularity to the entire upper half plane. So as always, usual the picture of fundamental domain. Now the key word in the question is it's a holomorphic modular form, which means that this is by definition at I infinity. So up here in the upper half plane fundamental domain at I infinity, it's still a holomorphic function, so actually has a value. Alternatively, if you think to a Q expansion, so Q is equal to pi I tau, and we're therefore in the picture with the unit circle for the upper half plane. This fundamental domain will be mapped inside some circle of radius less than 1. And in exactly the same way, the homomorphicity means that at the origin, it actually has a value. It's a well-defined number. So therefore, in the closure of F in the fundamental domain, this function is going to be bounded. That's what we want to claim. The reason it's bounded is F being holomorphic means it's continuous. And fundamental domain, or the translation of this to this circle of radius less than 1, is a compact set. So continuous image of a compact set is compact, that means it's closed and bounded. And so the comments, I'm finishing you off with the sort of topological notions of going to proving that continuous and mean compact thing is compact also, or you remember something from first year analysis courses or something. So that is just a standard fact once you realize that you're working with the image of a compact set. So now we ask about how this fundamental domain is translated across the upper half plane. Now pick any point you like for the tau prime in the upper half plane, and because we know the fundamental domain is a fundamental domain, we can write tau prime. Let me just try that the right way around.
Sorry, just about that. We use the fact that the expansion of Q only has non-negative powers.
Yeah, that's exactly it. I didn't write it out explicitly, but F is going to be some an q to the n and equal to 0. So at q equals 0, we don't have a pole to get an actual number out. And so on this fundamental domain, or this image of it as a unit, as something inside the unit circle, you actually have a value at every point. It's a continuous function. So, just make sure I get this to the one way around. I don't want to take tau prime is gamma tau or tau is gamma tau prime. Yeah, so I want to write that the image of some point in fundamental domain can be translated to any other point by some suitable by the action of some suitable matrix. So there exists gamma A and C B in SR2Z that takes you from some point in fundamental domain to the one you're interested in. So now we ask for value of f of tau prime. That's the value of f of tau. That's the value of the moment. So f of tau by modularity is going to be c tau prime plus c, f of tau prime, y t. I'm going to look at the value of f of tau, so that's equal to f of gamma tau prime, which is then equal to something like that. Now we've picked tau to be in the fundamental domain, so we already know from the previous part, the previous argument, that this is less than or equal to n, some upper bound I think of the domain. So the bound on fundamental domain is going to be capital N, say. I'm only writing n because trying to distinguish little c and big C in my handwriting is probably too much work. Then we look at behavior of this side and say that if C is equal to 0, then the matrix we translated by has to have the form of C is 0, therefore to get determinant 1, it's plus minus 1 on the diagonal, and then something up here, some P. Therefore, we're translating f of tau to f of tau plus B. And in fact, getting these things are exactly equal. This functions one period or on this automatic factor C tau plus D is just the identity. Therefore, if you take the fundamental domain and just translate it left or right, the value of the function doesn't change, so you get the same bound. Otherwise, we can assume C is non-zero, and then ask for the absolute value of C tau plus D, or get some bound on it. And I'm just going to take the really silly bound, writing that as root of, if tau is x plus iy, that is cx plus b squared, that's the real part, and the imaginary part is cy squared. That's definitely greater or equal to absolute value of c divided by y. So it's going to be greater than absolute value of y since c has absolute value greater or equal to 1. If c is non-zero and is an integer, let's have the absolute value greater or equal to 1. And absolute value of y is just absolute value of the imaginary part of tau. So very silly bound, but it's the one that's going to work. If I look back at what I wrote up here, Now have this is less than or equal to n. This is greater or equal to the imaginary part of tau prime. I guess I've changed from tau to tau prime. This is greater or equal to imaginary part of tau prime to k. Therefore, I get that my value at any point, any we find outside the fundamental domain is going to be less than or equal to this bound n times the imaginary part of tau prime to the minus k. And so combining the two cases gives you the bound in question. So then we should go on to part B. With that for reference. So part B is asking us to assume that F is a cusp form, so that this first coefficient A0 is equal to 0, and to show a better bound on the value. The idea, first of all, which doesn't rely on it being a cusp form, is to note that if you take up the value of the imaginary part, the value k, so about k over 2, and up to the value of f of tau. This is SL2 Z gamma 1 invariant. So as you translate us using matrices in SL2 Z, the value does not change at all. It's something to just directly check. I can part of maybe the imaginary part of gamma tau, this power, so value of f of gamma tau. Then by one of the earlier questions, this should be imaginary part of tau over this ordinary factor square, tau 2k. So this could be sort of plot and confirm that. This one I want to use. And then by definition, F is a modular form, plus form. So this will go to theta plus d to the k at the value f of tau. And we can just cancel that with the denominator around there as well. So this combination does not change as you move across matrices in SL2Z. So that's step one. Step two is to note that, well, step 2A is to note that this combination actually makes sense as tau goes to I infinity. It doesn't blow up, it actually goes to 0. And this is where we do need to use the cusp form behavior. So if I write tau equals x plus iy, then look at the Q series for f. We are looking at the behavior of y to the k over 2 and some n equals 1 to infinity, some coefficients an, q to the n, q is equal to 2 pi I tau, which is e to the 2 pi I x e to the minus 2 pi y. So since n runs from 1 to infinity here, we can pull out a factor of q and write this as some going from 0 to infinity an plus 1 q to the n, or whatever you prefer to write there. Just pull out a factor of one factor of q, and you have some remaining bit that actually goes to, stays bounded as q goes to 0. Now, as y goes to I infinity, q will go to 0, and you can see that this expression is going to give, it's going to be equal to so as q goes to 0, this just goes to whatever the first coefficient is. So we go to a1. The key point is this bit goes to 0 because you have this exponential factor that's killing the polynomial bit. So the function is bounded as y goes to I to infinity. And so with the same idea as before, it's now a thing that makes sense that I infinity, it's continuous function over, and then it's mapping from the compact set, so it has to be bounded. So you get that there is some absolute bound actually part of tau will go to times tau has to be less than some bound n. And now we're just combining this with a little bit of previous work. We know that this thing is invariant as you translate with a matrix in SL2Z. So at every single point you have then just take this object from domain, you get the same bound. And so the bound just holds on the entire half plane. And then to get the one in question, just divides through by imaginary part tau to the k over 2. So that is still back up to the question. We asked to show that the imaginary the bound is something times imaginary part of minus k over 2. So we've got that just by dividing both sides by imaginary part of k over 2. Then we can use this to look at the final part. It's asking us to give some bound on the actual coefficients of the cusp form. And so for that, we just want to start with the formula from Fourier series that gives us the coefficients of the Fourier expansion in terms of some interval. So f is going to be some an q to the n, and going from 1 to infinity, we're assuming it's a cusp form. So from there. Then we can write the following integral to get the coefficients of the cusp form. So we carry x plus I y. We multiply with this complex exponential and take the integral over x. And you get a formula for the coefficients of the cusp form. And now we want to take the absolute value. So it's going to give us that absolute value of an is absolute value of this integral, so less than the absolute value of the integrand. And then with the usual trick of writing, utility by in x equal to I n y. The purely imaginary bit there has actually value 1, it's not going to contribute. So the integral is bounded both by this integral. And then from part B, we know that since f is a plus form, this has the absolute bound, some m times imaginary part to the minus 2k, imaginary part of tau is y, so it's bound is m times y to the minus 2k. And then just do the integral. There's no integral to do because there's no dependence on x anymore. So we get the bound of minus 2k I n y. So if you remember this sort of discussion we had, that you could try to more directly write down the Fourier series, write down the coefficients of the Fourier series, and have to do some work to show they're constant. So see that thing here. In principle, there could be a dependence on y in the coefficients because we're taking Fourier series across x. And so we get a bound that still depends on y. That means we have a bit more freedom, and now we can just choose a convenient y, in this case y equals 1 over n, to give the bound that an is, after value of an is less than n equal to pi times y times n to the k over 2. And then all of this is just lumped together as one constant, and that gives the bound in question. That's how to deal with the last exercise on the first sheet. So what I'm doing now is go on to the second exercise sheet and then let's talk through some of the questions there. Just happy with that. So the first exercise is the one Daniel said we should do. They prove this summation formula. This we used to construct or find the fancies. Just basically made for reference. Now, there's probably a couple of different ways to approach this one. The way I'd maybe suggest is to use an identity, sort of partial fractions identity that Euler established to give an expression for pi cot pi z. Write that down. Maybe say in words how you would prove that as a separate thing. So, and make it take, maybe want to take some care with exactly how to do the summation on this side. I want the sum to run over the bounds minus n to n, so symmetric. We roll 1, 1 minus 1, 2 minus 2, 3 minus 3 all at the same time. And this formula should be valid, these conditions for z in r minus the integers, between both sides and to diverge of an integer. Maybe I just take this as a fact at the moment, numeric at the end, if you want some idea how to prove that. What we want to do now is take the derivative of this a few times, or rather expand out one side with the Taylor series first and then take derivatives. So I'm going to slightly sloppy notation. It says this sum is pi cot pi z, which you actually expand out with exponentials, should be 1 plus equal to 2 pi I z, 1 minus equal to 2 pi I z. And then we can tail expand. These if z, assuming z is in the upper half plane, you run into issues with z-act integers where divergence. So the problem is just expand by the geometric series, and so you should be able to quickly get that this is sum n equals 0 to infinity equal to I n z. And so after a little bit of rewriting, we've got that sum from n equals minus infinity to infinity and to z is the following. And now we want to differentiate that into k minus 1 times. So on the left-hand side, as we get a minus 1 to k minus 1 and k minus 1 factorial. We've got to change power. On the right-hand side, the half sum disappears, so we get sum n equals 1 to infinity. And the k minus 1. And now we can do a little bit of rearranging if I'm missing the 2 pi I outside, aren't I? Let's then do a little bit of rearranging. And you should just quickly get the formula we're supposed to prove. And we'll have to okay, maybe at some point we should take care to check these converge properly into interchange integration, interchange summation and differentiation. But somehow that's maybe bundled up in the proof of the identity we started with. So I maybe leave that exercise after that. Let's go back to the top to look through the list. So I will try exercise 2. With exercise 3, I'll already say, I maybe won't go through that in detail, but I'm going to try to give a bit more of an explanation for the SL2Z case, because I was very quickly just skimmed over the details, and then that would set you up much better to do exercise 3 here. But let's look at exercise 2 first. So with this, we're supposed to do essentially some sort of different way of representing modular forms of weight k in terms of Eisenstein series. It's going to be defined for E46 weight eternal E14, some power of this discriminant, and then some polynomial in the J invariant. Defined down there. So the idea to start this one is to now take this arbitrary weight we're starting with, so it's a multiple of 12 plus a remainder bit, and reduce it to something that's a multiple of 12 in weight. And then we have the discriminant function we can play with to deal with that part. And the extra remainder bit is then going to give this Eisenstein series bit. So maybe the idea is to use that the ring of modular forms is generated by E4 and E6. So we can write this arbitrary modular form we've taken and write F as some polynomial coefficient Cij, E4 to the I, E6 to the J, where the parameter 4i plus 6j is something up to whatever weight of the modular form it is. Now, if the weight is not divisible by 12 already, then we can note that despite there can't be just an E4 to some power term and an E6 to some power term. So we have to miss one or the other off. Otherwise, if we had both, then in fact we get the weight being divisible by 12. We're going to have something like this plus a load of intermediate terms. Six. So this is the case then where we can go by 4 and 6 until by multiple it's going to be 12. And we assume the weight is indivisible by 12. The whole point of this is now to say we can factor out some monomial bit, some non-trivial monomial bit. Let's say 48 to the B. And then this we factored out is going to give us the Eisenstein-Siemens bit that's appearing in the representation we wanted. And if you write it down a little bit more specifically, we have factored out something like E4, E6, E4 square, E4, E6, or E4 square, E6, the weight of 4, 6, 8, 10, and 14. And then that's going to give, you can check that each of these spaces is one dimensional, or forms of that weight is one dimensional. We'll then get that this is just some multiple of the first two are obvious there, 4, 6. What we wrote is F4 and F6 in the question would be some multiple of FA or E8, so FA, then F40. So the bit you factor out like this gives the Eisenstein space we want to prove in the representation. Now you can look at this modular form F after we want to start with, divided out by this F of K naught, the notation.
So not only you factor out has to be one of those.
It should essentially be one of this list.
I'm sorry, so one.
Well, at the very least, you can.
Or has to be divisible by one.
I guess divisible by one of those is probably the better way of saying it.
Right.
And that's why we've covered all possible remaining as modular. We're looking at here modular 12.
Right.
Like this. Let me just check the notation. Yeah, we called that remainder with K naught. So we've now got modular form F divided by some bit K naught that I know I can factor out. And since it was exactly divisible by this is going to be modular form of weight. The order K is 12L plus K naught, just from the statement of the question. So this is the modular form of weight divisible by 12. Now the trick is we have a nice modular form of weight 12, this swimming function. Let's just divide through by enough powers of that to get something of weight 0. So it's going to take F divided by F K naught times delta to the L. And so we now have something that transforms of as a modular thing of weight 0. I'm not going to say modular form because it's not. But the transformation under the actions that you said will have weight 0. So if you consider the Q expansion of this and what the maximum power of Q to the minus whatever the PA is, is going to have Q expansion starting from n equals minus L to infinity with some coefficients n Q to n. That's the maximum you could generate from dividing through by delta L times. But now if we recall the Q expansion of the J invariant that was written down sometime in the lecture yesterday. It starts with Q to the minus 1, plus 744 plus something else. So by looking at powers of J, it's going to start Q to the minus n, the n power is going to start Q to the minus n plus higher order stuff. So it means we can just brute force match up whatever this polar bit is and eliminate it completely. So we look at the constant term, and it's naught. And so we do this matching by some polynomial in J of we less than equal to L. And then the final claim we check is that that is everything that can possibly arise in this way. When we now get rid of this bit, we've matched up the entire expression. So now what we know is that this modular form started with divided by delta to the L of K naught minus, and then like PL of J to this polynomial. It's going to have a Q expansion that starts at n equals 1 to infinity, some coefficient Cn Q to the n, doesn't matter. Because I've killed everything, all the poles and the constant term, which means it's polymorphic. There's no pole Q equals naught. But we also said it's modular with weight 0 because everything transforms as soon as it's modular with weight 0 here. And there are no modular forms of weight 0 except for constants. And the constant here we eliminated that. So this entire thing is constant, and constant is 0, is equal to 0. So we've written F as some polynomial in J, this Eigensimultaneous bit, and this discriminant function to the power L. So now it all works. let's go back to the questions at the top. I don't know whether it's worth looking at exercise 3 now or exercise 4. As in exercise 3, I'd more try to give an explanation of the Lenz's formula and very quickly went over yesterday. So I wouldn't actually solve this question. I'll just give you the reminders and preferences. Okay, then maybe I do exercise 4. This is a bit more fun. So in exercise 4, we're asked to show that this group gamma 2, which was matrices A, B, C, D, congruent to the identity. Mod 2 is generated and actually freely generated by these two particular generators. So there's sort of 2 steps here. First of all, we should show that it's generated by those. That takes a bit of work on its own. And the second step is to show that there are actually no relations amongst these generators. So I can try to indicate why it's generated by those in sort of 2 different ways, just to give you some options. And this before the generators A and B. So first I have to show that gamma 2 is generated by these 2 matrices A and B. One way to do that, one idea for that is to do something similar to what we did for SL2Z, try to construct more algorithmically fundamental domain and show that these 2 things satisfy our need to move every point of the graph plane into this fundamental domain. So idea 1 is, then you already told us the fundamental domain looks as follows. The strip -1 to 1, we've removed 2 set circles from the bottom. Now, if you take some random point in the upper half plane, you can certainly use matrix the generator A, so the translation by 2, the sum power to shift tau into the strip with real part between -1 and 1. So maybe as they do these columns of 2 would eventually land somewhere in this strip. And if you're the iron fundamental domain, great. If you're not, you have another thing to play around with, this inversion. And same ideas as yesterday, you should be able to give an explicit proof that if you don't land in fundamental domain, therefore you are somewhere down here or here on these points. Then applying the generator B and repeating will eventually land you in after a finite number of steps. We will force the imaginary part to be bigger and then you iterate and bigger and then you iterate and so on, only finitely many choices. When was step 1 yesterday, we repeat step 1 with tau, and then just keep iterating. And there's lots of things that you have to check explicitly, but the same idea as yesterday is the key thing. Method 2 would instead be to explicitly take any matrix you like in this group. And use these generators in a clever way to reduce some norm of the matrix until that eventually you have to get down to the identity matrix. So then I won't go through the explicit details, but give you enough of an idea that you can make it go yourself. To use the acting on the left with some power of first generator. Okay, I have notation. I have A as a matrix and A as a coefficient. It's going to change the top row of the matrix by some multiple of the bottom row, so it gives you A plus 2n, A plus 2nc, B plus 2nd, and the bottom row again. And choose n in such a way that you reduce the sum of the squares of the entries. So roughly the idea would be to then look at the sum of the squares of the entries here. If you expand it all out, you should get something like a squared plus b squared plus c squared plus e squared, plus a bit that then has a factor of n. So something like 4acn plus 4bdn, 4c squared n squared, plus 4b squared n squared. And this bit is now some quadratic polynomial in n. You can see that it has a 0 at n equals 0, and it then equals the sum of the combination of A, B, C, D. Which is AC plus BD over C squared plus B squared. So now, if you can find an integer that's between these two, and plug that in as the value of n, you've got something where this sum is being reduced. And if you keep repeating that, you'll eventually get down to some list you can enumerate and check that you have to land at the identity matrix. Find an integer between that and that. It takes a bit of work to show that there is an integer in that range, but you can do it, and you can do it relatively explicitly. But if you keep going like this to reduce sum of squares of matrices, you either end up acting with this 1, 2, 0, 1 some number of times, or the 1, 0, 2, 1 some more times. One of them reduces the norm of the top row, one of them reduces it for the bottom row, so you just keep sort of alternating between the two until you've made the sum of squares of the matrix as small as you can. And so you eventually, it's something to check, but you will eventually get the identity matrix out of that process. And so that shows you that the group GAN 2 is actually generated by the two things that we're supposed to show it's generated freely by. So going back to the slightly bad notation at the start, it is now generated by matrices A and B. Next thing we need to show is that it's actually freely generated. And that'll be the last thing I do here, and again, I'll go through the ideas of it. So we want to show that there aren't any relations between A and B of these generators. For that, we need to use the hint in the question. That takes it a bit further down. And the hint is to use something that's called the ping pong lemma. So let me explain what that is now. The idea is to note that these matrices, the first one A, the second one B. Just note that these matrices act on the objective line, and in particular, they do something to the regions X and Y that have been labelled in question. So X is the interval from -1 to 1, Y is the complement to the endpoints. Picture X is that. X is that. And different colour, Y is what's left, including the point of infinity. And the key observation is that matrices A and B will flip X to Y and Y to X. So if you apply matrix A or B to X, you land in region Y. If you apply it to Y, you land in region X. So A and B just keeps doing this interchange. So now, if you suppose there is a relation, suppose there is some relation, it's going to be in the form A to some power, some integer, times B to some integer, times A to some integer, times B to some integer, and so on and so on. Then you can very quickly deal with cases where it starts with an A and ends with an A, or starts with a B and ends with a B, as follows. So we know a relation of something like A to the K1, B to the K2, dot, 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 B to the Kn minus 1, A to the Kn, or these Ki are non-zero, they might be positive or negative. The thing is, if this is the identity, this relation on the show it can't exist. Look at how this relation would act on the set X. You feed in the set X on this side, and matrix A or A2 is going to flip it around to the set Y, and B is going to flip it around to the set X. So then B is going to keep doing this, and B is going to flip it around again to X. And finally, the last A is going to flip it around to Y. But clearly, the identity matrix isn't going to do that. The identity is going to take X to X and Y to Y. And you have exactly the same issue if you started with a B and ended with a B here. You make that B to some power, and you end with a B to some power, even if it's next to Y, some of the times, and you'll be in the sort of alternate set. Now, yes, that's why it's called ping pong, because you keep going back and forth between these two sets. So that deals with all of the simple, obvious issues. The only thing you have to worry about now is what happens if there's some relation that starts with an A and ends with a B. So, what about A to the power K1, blah, 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 B to the power Kn equal to the identity? Well, this will, if you try to see what happens to X and Y here, you go from X to Y, X to Y, you land in the correct set at the end. But there's a really simple trick you can do here. Since the group is big enough, you can multiply on the left and on the right by some sufficiently large power of A, say, in such a way that you don't eliminate the first term. So multiply basically to the absolute value of K1 plus 1, something silly like that. Times this word times A to the minus absolute value of K1 minus 1 on the other side. And then suddenly you have a relation that starts A to something non-zero, dot, 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 or all the same stuff as up here, filled in there. B to something, and then another A to some power that's non-zero. And then we do this to the identity down left by some power on the final right by they just cancel. So you still get the identity there. We're still got the relation that we already showed can't exist. So that just deals with finding the remaining case. Can't be any relations between these elements, and the question was done. So I think that's probably a good place to end. Scroll back to the top and see what's missing. I haven't talked about exercise 3 yet. I mean, maybe it's worth doing it tomorrow, just a bit more detail. And I think exercise 5, Daniel actually wanted to say something about himself. It's a fairly long one, and is, I guess, a bit more on the analytic side of things. But it's supposed to give an ultimate proof that the space modular form is finite dimensional. I'll let him say something about that. And thanks.